I thought so. Oh, is it not? Then if I don't do it, not right off the top of another class, then just go ahead and send me an email. If you want to send me an email right now to do it, I'll make sure it's visible on my fire. It's on acids and bases. Okay. It's on acids and bases. What is an acid or a base? What's an acid? What do you know about acids? Pardon? Or it has a pH level less than 7. Okay. And you can actually, in theory, get below 1 as well. In vivo, it's not as important. You dying, that happened. Well, your stomach sometimes can get as low as getting closer to 0. Okay. What else is an acid? What makes an acid an acid? It's going to lose protons, and it loses it as an H+. Because if you think back to the hydrogen, when it's an ion, it only has 1 electron to lose. It loses that 1 electron, and the only thing left is a proton. And so that's why they even abbreviate the protons as an H+. Okay, so here. And many times, and on the PowerPoints they go into a lot more detail, sometimes they also abbreviate it this way, H3O+, because once you put that proton around water, it's going to hook up with the water to make H3O+. The H3O+ has a special name. I wouldn't ask you to memorize this, but just in case you see it, just because, well, you may, it's called hydronium. Whoops, that's supposed to be an H. Hydronium. But they use those interchangeably. I'll just say that just in case you see it in the sample problems. They'll also try to put the example problem PowerPoint on for chapter 14 up as well. So they may use H+ and H3O+ interchangeably. Especially in vivo, in our body, we typically don't see H+ by itself because we're water-based. So it would probably almost always will look like H3O+, because there's going to be a water around. Okay? Yes. Technically, there are 3 definitions for acids. So the definition, there's one that's called the Arrhenius. And it's not so much that the name is the important part, as in what the definition is. And that's the one that you usually learn probably in, maybe in school, growing up and stuff. And that's the one that whenever you put it in water, a proton dissociates. So this is proton, or the H+, dissociates in an aqueous solution. Or another way to say it is you can say acids lose protons. Another one which you may have heard, depends on how much chemistry you've had, it's called the Bronsted-Lowry. That the name once again isn't so important as in the idea. Okay. And technically that is, I think Bronsted was Swedish or something like that, and so that's why that's the way that it's spelled. And what Bronsted-Lowry is that the simplest way is that an acid is a proton donor. It's essentially the same thing, except it also, you can use the Bronsted-Lowry definition without water being around. Okay, because Arrhenius way back in the ancient days, they typically only talk about water. That's what they do about. So with respect to acids and bases, whereas this one you could use it in any type of solution. Okay, it doesn't have to be a water-based solution. Okay, there's a third one that I'm not for sure. They may just make a passing reference to that I'm going to let you know about, and it's called a Lewis acid. The first two all looks at it with respect to the protons. Lewis acids look at it with respect to the electrons. Okay, and so a Lewis acid is, so I'll rewrite this. Lewis acids are electron acceptors, And once again, I just want you to know that in case they mention it. In vivo, they're very important. Because now this even, they talk about Lewis acid a lot of times in medicine even, because of the fact that usually when you're doing chemical reactions, we're talking about it with respect to the electrons instead of the protons. The first two are referring to acids in terms of the way that they are related to protons. Lewis one refers to them with respect to the electrons. Okay. So those are acids. I'm going to go ahead and then just talk about bases. Since we talked about acids and then talk about bases, then we can go back. And that's way. So that was an acid. Now we have bases. And we'll give examples of each. Okay. And once again, you can use it with respect to Arrhenius, with Bronsted-Lowry, and with Lewis. Okay, with all three. But what do you know so far about bases? What are bases? If acids have to be below pH 7, what would make a base? Above pH 7. pH 7 is neutral, it's equalized. Ideally, if you have the exact amount of acid, same concentration and everything, same concentration of an equally but opposite strength base, they're going to neutralize each other and become pH 7.
That's spit. I know it's so random, but what's the pH of spit?
Pardon?
What's the pH of your saliva? Is that neutral?
No.
Or is it more acidic?
No. Typically, it's going to be a little bit more acidic to help. Okay. And some of it's also from the fact that you have stomach issues that can come up too, and it's going to even lower the pH even more so. Okay. Do you want to know what's the pH of your blood typically? Roughly, if you're healthy, what is it roughly?
Is it like 7.6?
It's right around 7.4 or 7.5, 7.6, yeah, right through there. It's slightly alkaline, yes. It's slightly alkaline. Okay. So it's not perfectly neutral. But your stomach is very acidic. It's anywhere from like pH 0-ish to pH 1 point something. Your intestines are still slightly acidic, but much more basic than the stomach. It's usually, if you're healthy, it's right around pH 6 to closer to pH 7. So that way it helps neutralize your stomach acids. But, okay, those are the kind of questions that we're talking about in medicinal chemistry or biochemistry. All right, but what else about bases? Not only about the pH, but what do bases do? What do they have to do with?
The opposite of all those.
It is, okay, except for, it is the opposite, but it's not called an antiproton or anything like that. It's hydroxides. So, for Arrhenius, I'm going to do this in the same order. Arrhenius, once again, he was looking at it, you stick it in water. Okay, you stuck it in water, and what was given off was a hydroxide anion. Okay. So in an aqueous solution, OH minus is dissociated or is given off. So that's why when you have an OH minus and it hooks up with an H plus, it makes water. The acid and the base makes water. But that's really a simplistic one, and it only explains a handful of bases. Okay? And typically those are the strong bases like sodium hydroxide, potassium hydroxide, things like that. But a lot of your bases in vivo, inside your body, may not be hydroxides. So that's, many times, those are strong bases and even tied, keep it all over. And so we have like amines, for your amino acids, amines, those are the groups that typically in vivo are basic. And carbonate, okay, that's helps do your pH of your blood. Okay. So then we have, what color to use? The Bronsted-Lowry definition. And it really is the opposite. Instead of being a proton donor, it's a proton acceptor. So that's why when you say H plus an OH group makes water, that OH is the base because it accepts that proton. And then we have Lewis that came along, and Lewis said, you know, that's great. Well, he didn't say it this way. I'm saying it this way. This is great with respect to protons, with both those, but there are reactions that occur that have nothing to do with protons, that have to do with electrons. And so, whereas before, the Lewis acid was the electron acceptor, Lewis bases are the electron donors. I'm going to abbreviate electrons like this, just first. And I forgot to put it up there on the ender for acids, but once again, this was where pH, the pH is greater than 7, whereas in acid, the pH was less than 7. And we'll talk about in a moment where that 7 comes from and what the P means. I'd be kind of surprised, actually, if you knew, because I don't know what kind of math it came from, if it's from some type of algebra or something. Okay. Yep.
If your body is a little bit more basic than it needs to be, will the acid in your body, like, is there a system in your body that you're going through?
Yeah. It's called buffering. You have buffers.
That's right.
And you've got multiple buffers. What is the number one buffer for your blood? This is actually a really good example for what we're talking about here. Let's say, well, actually, that's vitamin water. But if I had my normal diet soda, that's really acidic. Or if you drink coffee, coffee is acidic. And so if you drink it, why don't you die? Right? You know, eventually some of us, when some of the fluids and stuff will go into your bloodstream, or if you have certain intravenous injections will not be pH 7. Okay? So if it goes into your bloodstream, why don't you die? What happens? If it's acidic, there's got to be a base nearby that can help buffer it. These are called buffers. You know what buffer that your blood uses? And it's a different one than your cells use. Okay? Your body's very, very specific the way we were designed. Your body uses something that there's a lot of. So everybody inhale. Nope. Carbon dioxide. Okay, so carbon dioxide, if you remember, it's a gas. Carbon dioxide is a gas that it's not very soluble. However, we have an enzyme in our body called carbonic anhydrase, and it's actually one of the ones that sometimes they use for metabolic disorder, like to test you. And so it converts carbon dioxide to bicarbonate. And bicarbonate, it can be both an acid and a base. And so that bicarbonate, which is based off of carbon dioxide, it helps regulate it and keep your body right around that 7.4 to 7.6 pH for the blood, for your serum. Now for the cells, they use phosphate. Okay. So cells use phosphate as a buffering system, but bicarbonate is used by your blood. Okay. Then another term that they like to use, or that they use, is called, and I'm just going to put it here because might as well. It's called diprotic acids, and the di means 2, and technically you can also have polyprotic, which means it has more than 2 even. And all it means is there's more than one hydrogen that can pop off. Okay, so one example of that is the bicarbonate that I just was talking about that your body uses is H2CO3. And it is reversible, which is important since our body needs to be able to go back and forth. And so it can lose that first one and become HCO3. And then it could, if it gets extreme enough, you lose that second one to become CO3 2-, to be carbonate. So the one in the middle is called bicarbonate. One on the end is carbonate. So bicarbonate, carbonate. And so as you can see here with the bicarbonate, it can either gain a proton or lose a proton as needed to help keep your body in the right pH. So that's why it's called a buffer. And it's not shown here because this is the chemistry one, but the way that our body makes that is that CO2 in water. As you can see, CO2 plus H2O would make H2CO3. And so we have an enzyme that takes carbon dioxide, reacts it with water to make this. Okay. My old boss, actually, she became world famous for working on the enzyme that does it. It's called carbonic anhydrase. And so she actually just recently was named to be the provost or be the head of Texas A&M University. And so, yep. Okay. So it's diprotic. You can also have dibasic bases. They're called diprotic because protic means two protons. But the only big, and one example of that would be like calcium hydroxide. So if it's a dibasic compound, but there's one big difference. So like, for example, CaOH2, whenever it only does it all at once. It's not one at a time. And so typically, they don't make good bases. I mean, they don't make good buffers. It's going to be all or none. There are some exceptions. One exception that's used in medicine a lot is milk of magnesia, which is a magnesium hydroxide based one. And so it reacts with extra acid in your stomach to help neutralize it. That's how it works. Okay. Calcium carbonate is used a lot of times in antacids. Okay. And so it can also react to make bicarb, which can then be used normally in your body if you have too much acid in your body. Okay. Just some other, and I do not try this at home. It always gets me, I always want to laugh whenever, and if you look at when I put the PowerPoints on it, they'll tell you about the way that acids and bases feel and taste. Please do not go and try to, there's some that you can, you can bite into a lemon, right? But there's bleach, don't drink bleach. So someone obviously did a long time ago. But just in general, acids going to be, your choices would be sweet, sour, or bitter. What is an acid going to taste like? Sweet, sour, or bitter? I'm saying no. That was a multiple choice question. They're sour. They're sour. Like, lemons are sour. Lemons are sour, so acid. That's citric acid. All right. Whereas a base is bitter. That's what gives. Even though coffee overall is acidic, typically. If you cold brew it, by the way, it's less acidic than if you do hot and warm brew. Just FYI. But coffee is acidic. However, there are bases inside it that give that bitter taste. It's called alkaloids. And your book talks a little bit about, and it's, take it what it is, because it's a secular book, but it talks a little bit about how they say that this is perhaps like an evolutionarily conserved phenomenon because a lot of the poisonous plants are alkaloid based or bases. And so our tongue, the moment we touch something that's basic, it tastes really bitter. So that way the whole idea is if you try to pick up that toadstool or whatever, you want to spit it out. So don't eat toadstools. What? Toadstool, poisonous mushroom? Okay, don't do it. Okay, so another one is the way that they feel. So, and this one you may know, a bleach is a common base, or if you're working with ammonia cleaners, how do they feel if they get on your skin? It's kind of slimy, slick. So bases tend to be really slick, and the reason why they do burn, and the reason why is they are doing something called saponification to your skin. They turn the lipids in your skin to soap. Okay? But yeah, that's not good for you. Okay, but that's actually how they used to make. That's how we. So whenever I taught organic chemistry, we would make our own soap, where we would take different. We would use our skin, but we would take different oils that are lipids, and we would add a base to it, and it forms a detergent. So then it solidifies. That's in the old days. That's what they would do, especially like whale blubber, which is just fat, and then they put in lye, which is the base, and then you get detergent. Okay, so that's why they feel slick. But please don't go and try to fill. And then it talks about litmus paper. One of them, it'll turn like, base will turn like blue, acid turn pink typically. Okay. All right. Oh, what's sorry, this went to sleep. One thing that I want to do in your book, I think it tells you to memorize it, but I wanted to show you where it comes from. You can do it. You can wake up. Is how do they get pH? Like, what does that mean? So, what it comes from is the following. Let me use a different color. Oh, oops, sorry. It comes from water. So this whole idea that, you have an H plus an OH minus, it goes to make, it is equilibrium, go frontwards and backwards, to make water, okay? So if you have absolutely pure water, and you measure how much H plus is there at equilibrium and how much OH minus is there at equilibrium, it's going to be neutral. And what they noticed was the concentration in molarity. Let me write this out. And by the way, I think I forgot to put this on the example on that video or on the paper. One way that they like to abbreviate for molarity, especially for molarity and concentration, is they put them in square brackets like this. That just means concentration. They have to be equal to each other, and they're equal to this number. It's 1 times 10 to the minus 7 molar. That's a ridiculously small number, right? If you write it all the way out at 0.1, 2, 3, 4, 5, 6, 7. And so there is a mathematical function. I don't know where it comes from. I'm sure mathematicians would be able to tell you exactly historically where. But just like if I gave you the little cross sign, like that, looks like this, you'd say, well, that's a plus, right? And the little dash is a minus, and you know what to do with that. And the x means multiply, and, well, divide means divide. I don't know how to, without drawing it. Well, there's a mathematical function called p. Okay. So, and I don't know where the p comes from. I have no idea. Okay, so what it does is literally, there's this little p, and they call it, for concentration, this would be the mathematical function p of the concentration of H. And what that is equal to negative, whoops, that's supposed to be a negative sign, negative log base 10 of the concentration of H. So that's why, in theory, we could have a P students, and P would be negative log base 10 of the number of students. It just doesn't make sense. Okay? The reason why that they do this is because they can take numbers that are either really big or really, really small and make them manageable. Okay? So if you solve for this mathematically, you put this in terms of P, it becomes 7. Okay, so that's why, in reality, whenever we talk about the difference between your stomach and the acid in your stomach and pH 7, we say, oh, pH 1 and pH 7 doesn't sound like a big difference. But you have to realize that that's log base 10. And so a pH of 1 literally would be 10, because that's 10 to the power. And so, it'd be 0.1. It'd be 10 to the negative 1. So, power. And so 0.1, the difference between 0.1 and 0.0000001 is a big difference. Okay. So that's why anytime that we talk about differences in pH, you have to realize that we're talking about it on a logarithmic scale. Okay, and so that's why this right here, show you an example. This will, well, let's say 10, and I put the decimal point in there just so that way you can tell that it's clearly 10. And we want to do 0.001. Okay. We know there's a big difference. That's 1/1000th versus 10. So if we put that in terms of P, the second one, if that was pH, then that would be equal to 3, if that was the concentration of H. Okay? Whereas this, if this was the concentration of H, then that pH would be equal to negative, let's see, 0 is 1, negative 1. I'm sorry, yeah. Okay, so, because it's a negative log base 10. That's why I just wanted you to get an idea that even numbers, like the difference between pH 3 and pH 4 doesn't sound a lot, but it really is. It would be the difference between 0.001 and 0.0001, between 1/1000th and 1/10,000th. And so that's why they use the P just to make these numbers more manageable. It'd be a pain to always write out 1 times 10 to the minus 7, or 1 times 10 to the minus 7.41, if you were talking about the pH of your blood. It's just easier to write 7.401. Okay.
In what cases would you have a negative pH?
There are, in your body, you shouldn't. Okay, that I know of. I don't think that, not for a healthy person, you shouldn't. There are times that you could get to the negative numbers, probably in synthetic things, because I think hydrochloric acid, which is one of the strongest acids that we know of, it has a pH of right around 0, to maybe just a little bit below 0, because it just completely dissociates. Okay. All right, and we do have some hydrochloric acid-based stuff in our stomach. It's just that there are other bases and stuff like that in your stomach to kind of help modulate that. And your stomach also has to replace its lining. If you know from anatomy physiology, it replaces its lining all the time because the acids in your stomach eat it up. So, okay. Ooh. Are there any questions so far? Okay, let me see. If there's anything else that I was wanting to show you, to explain before I just show you some pictures. Because what we're going to do on Monday is, PW, yes. Actually, let's just do, okay. So, let's do a couple more terms, because whenever they talk about something being a strong acid or a strong base, it means they completely dissolve in water. And I'm saying water because, once again, physiologically that's important for water-based. Okay, so some of the examples, I'm going to do the bases first because there aren't that many. These typically are the hydroxides. It's on the first and part of the second column on the periodic table. So examples would be sodium hydroxide, lithium hydroxide, potassium hydroxide, strontium, barium, things like that. Strontium hydroxide. And the list goes on like that. But you can see there's a nice pattern to those. Strong acids, it's not as easy to tell. Okay? Because you can't just look at this column on the periodic table and say these are all strong acids. You probably already know that hydrochloric acid is a strong acid because it's common knowledge. But hydrofluoric is not. It's a weak acid. Okay, so there's only a handful of those that are strong. So it's from hydrochloric on down. So examples of those would be hydrochloric acid, hydrobromic, and hydroiodic. And then there's a couple of ones that are important, both for medicine and synthesis, and that's sulfuric acid and nitric acid. Okay, there are others that exist out there, but those are probably the big five. Okay. Just like the hydroxides are all of these except for hydrogen, that's water. All of these hydroxides would be strong, and these down here. Magnesium is not a strong base in that sense, because we use it medicinally. And there are shades of gray, just like with anything. Okay, but one of the reasons why I wanted to say that is because what we're ultimately going to be able to do is based off of their. So let's just do an example. If we had something like HCl plus NaOH. Maybe that was a neutralization reaction. And it makes NaCl, which is salt, plus water. You could even, remember this chloride and the hydroxide, the chloride and the sodium, they're spectator ions. They're not doing anything. You're literally just making salt water. This is a neutralization reaction. So if you know the concentration of acid, you can actually figure out what the concentration and the amount of base that you're going to need in order to neutralize it. Okay. And so that's going to take more time than what we'd have today. But what we can do is just plan it out. So now we can actually determine the amount of acid or base needed for neutralization, to do neutralization. So for example, I could give you a pH and say, okay, now let's figure out how much base we have to have, an acidic pH, figure how much base that you need in order to neutralize it. Or vice versa, we give you something that's basic, see how much acid do we need to neutralize it. So, based off of what we've already, these are really easy to balance, because it's always a 1-to-1 ratio right here. So as long as you know the molarity and the volume, you can figure out the rest. That was the whole purpose of the practice for the, not all, but almost the purpose of the practice for the assignment you just turned in. Okay.